Hey folks, welcome back. We're talking about dynamics. We're looking at plane motion, and today we're going to talk a little bit about general plane motion and do an example. So the physical system that we are looking at is this one here, and we're given that crankshaft AB rotates in the clockwise direction at a rate of 2,000 RPMs. And we're asked to find the angular velocity of bar BD and then the velocity of the piston, which we represent as V sub D, right? So the rotation is, again, going in the clockwise direction, and that is going to push the piston, which rotates the bar BD in the opposite direction, right? And so we are going to use our relative motion strategy and see if we can solve this. One of the things I wanted to try with this particular video is to give you an opportunity to see if you can figure out which equations that we're going to need in order to solve this. So I recommend pausing the video. Let's pause it for a few seconds, see if we can figure out which equations we're going to do. Okay, all right, well, I hope you paused it. I think the equations we're going to need are the relative motion equation, so VA equals VB plus VA with respect to B. Okay, and I also think that we're going to need the equation that relates linear velocity to angular velocity, right? So the one from the definition of the arc length, right? And that is VA with respect to B is equal to AB, which is how I represent vectors, times omega AB. Right? And what that does is that converts the angular velocity to the linear velocity. Pretty straightforward. I also think that we're going to need the law of sines. So what would that be? That would be sine A over A equals sine B over B equals sine C over C. Right? I think we can get there with those. So let's see if we can solve this. All right. So first of all, this omega AB is in units of revolutions per minute, so we need to convert that. So let's see. Omega AB is equal to 2,000 revolutions per minute. And we need to multiply it out so that we get radians per second. So 2 pi radians over revolutions, right? And the strategy is simple, right? You just put the one that you're trying to eliminate diagonal to where it's currently at. So for minutes, we would say 1 minute, put that on top because we're trying to get rid of it, and it is equal to 60 seconds. Okay, and when we multiply that, we get that it's equal to 209.44 radians per second. Okay, and if we look at the diagram that we're given, then we can see that VB is equal to AB times omega AB, right? And that's just 3 times 209.44, and when we multiply that out, we get okay, 628.32. So 628.32, and this is given in units of inches, so inches per second. Okay, And looking at the diagram, we're given that this is 40 degrees. Our velocity is normal to that, and so this is VB. So from the horizontal, we can see that this angle right here is 50 degrees, right? And we can add that. So 50 degrees like this. There we go. And we do that because we're going to need it in a second. So we have a defined vector for our velocity, right? We know the direction and magnitude of it. And we know the direction of our v sub d, that's going to be along the horizontal. So we can draw our diagram, right? So let's see, that is quite a bit more vertical than that bar is. So we draw it like this, and let's see, we're after this guy, right? So this is v sub d, and that is equal to the translation part, right? Both of these being v sub b, plus the rotation part, okay? And that is, what are we at here? This is v d with respect to b, right? And that is just the rotation about point B, right, where point B is fixed. And I guess I could put in letters here. This is D. This guy's moving there. So this is V sub B. This is point B. And this is point D, right? So in general, this aligns perfectly with this equation, right? So we have VD equals VB plus VD with respect to B. Okay, and from the video we just watched, we also know that we're going to need this other relationship. But first things first, let's draw the triangle, the velocity triangle for these three, right? The three of interest to us are the ones that come from here, right? So draw this kind of big. So this is v sub d. This is our ultimate target. This here, so it looks like that. This is v sub b. And this right here is velocity of d with respect to b. All right, so we found the 50 degrees. Right, so in order to solve this, we need the angles, right? And note that in our the triangle that we were given, and let me grab a different pen here so that this doesn't get too busy. But in the triangle that we're given in the diagram, then we have this relationship here, right? And this is 3, this is 8, then we have B, A, D, and if we impose a point B and draw a line, or excuse me, not a point B, but a point E, right, then this is 40 right here, this is beta right here. Oh, what we can say, if we look from this side to that way, then BE is equal to 3 times the sine of 40, right? Similarly, if we, cover this part and look that way, then BE is also, and I'm just going to put equals here, it's equal to 8 times the sine of beta, right? And we can use this relationship because this, if we just divide 8, then beta is the inverse sine of 3/8 of the sine of 40, right? And when we do that calculation, then we get that beta is equal to, let's see, I just did it, it was 13.948 degrees, which is close enough to 13.95 degrees. Okay, well, that tells us that this angle is 13.95, and if we impose this v, the velocity of d with respect to b, then what that means is that this vertical angle right there is also beta, right? So if you can imagine here, just trying to solve this, you get beta right here, right? Which means that this angle here is 90 minus beta. So 90 minus 13.95 gives you 76.05, right? So this right here, 76.05. Okay, and if that's true, then this angle down here is just 180 minus 50 minus 76.05, and that gives us that this angle down here is 53.95 degrees. Okay, and that allows us to then use the law of sines, right? So what would that relationship look like? That, let's see, let me draw a line right here just to keep this from getting too busy. There we go. So law of sines is, let's see, the sine, we'll start here, right? The sine of 50 over VD with respect to B is equal to the sine of 76.05 over VB, but we have a number for that, so 628.32 is equal to the sine of 53.95 over VD, right? And from here, we just take turns, right? Because we need to solve for omega BD, which we get from the velocity of dB. So in order to get to solve A, we do, let's see, these two, and in order to get B, we use these two, right? So for A, then we rearrange these, and we get that VD with respect to B is equal to, so these are just going to switch places, right? And so that is equal to 628.32 times the sine of 50 over the sine of 76.05, right? And that gives us that the velocity of D with respect to B is equal to, let's see, 495 point, I got 948, but let's just go with 95, right? And this is a V, so this is inches per second, okay? And in A, we're looking for the omega, so we use this relationship, and just looking at it, the omega AB here is equal to the velocity divided by the radius, right? So omega, in this case, what would it be? It would be dB is equal to, or BD, I guess, I'm sorry. BD is equal to this divided by the length, and that is 8. So 495.948 divided by 8 let's see, 495 point, we're going with 95 divided by 8. What is that? That is 61.9938. So let's just go with 62. So 62, that's radians per second. And if you get lost on which direction this is rotating, just consider that VD is going that way, this is going this way, so it's rotating in this direction here, so anti-clockwise. Okay, so that is part A. All right, part B, similar idea, we're just using the law of sines, and we get what? That VD is equal to 628.32 times the sine of 53.95 divided by the sine of 76.05. So I'll just calculate that real quick. So 628.32 times the sine of 53.95 divided by the sine of 76.05. Punch that in correctly, then I got 50, it is VD is equal to 523 point, it says 437, so we'll just go with 4.4, and this is going to be inches per second, right? Yeah, so you could get it in feet per second, or convert it to whatever, but there you have it. That is the relative motion strategy for solving this problem. I'm going to come back in a future video and we will solve the same problem using the instantaneous center of velocity method. But this is a perfectly valid method. It is simple, straightforward, and it allows us to use the velocity triangle, which is often quite advantageous. So I hope that was helpful, and I will see you in the next video.